Introduction. This project implements a parking lot counter with 4 sections A, B, C, D, each containing 8 parking lots 7 to 0. The counter tracks available parking slots, updating based on vehicle entering decrement and exiting increment.
State diagram and encoding. The state diagram represents the transition between the parking slot counting cycle both A000, A111, B000 until B111. Each state is encoded to the 3-bit binary format per section. A starting from A00 until A111, B000, B111, C00 until C11, D00 until D11. For the information, to number, we're using the 3-bit system binary, and the alphabet, we're using the 2-bit binary and making a combination circuit for make it alphabet display on 7 segment.
Flip-flop selection. JK flip-flop are chosen for their toggling abilities, reducing the need for additional combinational logic. They efficiently handle sequential counting, making them ideal for the parking lot system.
Truth table. Define the present state, next state, entry or exit condition, and JK flip-flop input for the accurate counting.
This is a Boolean expression, or K-map simplification.
Circuit diagram. The circuit diagram designed in quarters 2 implements the Boolean logic for counting available parking space per section.
Advantage and disadvantage. Advantage: efficient parking management, real-time slot tracking, and simple hardware implementation using JK flip-flops. For the disadvantage, propagation delays may affect real-time updates, requiring debounce logic for switch. Issues and challenges. Challenges include ensuring synchronizing counting, minimizing hardware delays, and debugging circuit connection in quarters 2.
Objective: to design and implement a sequence circuit using a JK flip-flop and logic gate to the accurate track and display the number of available parking slots across a multiple zone. To develop a functional state machine that transition between parking lot zone A, B, C, D based on the car entry and exit input, ensuring the correct state transition and the reset condition. To apply K-map and Boolean logic in the derivative Optimus flip-flop input equation, ensuring efficiency, circuit design, and reducing unnecessary logic complexity. This is a flowchart for the project. We start, and after start, continue to making a state diagram, transition table, K-map, Boolean expression, and circuit design. After circuit design, we continue to testing, and if we get the error, we try to troubleshooting, and if the troubleshooting is success, we continue to testing again, and if all success, we get the perfect result and the project is done. And this is our result from the waveform. So we start from the counting down. So if starting with the counting down, the ABC represent in 7 segments for the number, and AA, BB, CC, DD, EE, FF, GG for presenting the alphabet on the 7th segment. So that's mean first clock, if the input is down, so the present is A will be high, A, B, C high, D, E, F, G will 0 active low. So that's mean the circuit will making at active high, so A, B, C will present the 7, and the A, B, B, C, C for the first clock will present B, because from the A0 will be continued to B7. So B7 represent the AA, BB, CC, DD, EE, FF, GG high. So that's mean all insoluble segment will be high, and so the output will be present the B7 because the first counting down, and second clock for the counting down will present C high, D high, E high, F high, G high. So that's mean we present the number 6, and AABB will present the same because from the B7 will be continue to B6, B4, B5, B4, B3, B1. So the difference just the number, not for the alphabet. And if we continue for the clocking up, at the first clock for counting up, we present A high, B high, C high, D, E, F, G 0 are low. So that's mean we present the number 7. And for the alphabet, we present at the D, E, F high. Oh, sorry. For the first clocking out, we present A, B, C high, and for alphabet we present A, D, D, E, E, F, F high. So that means we will continue to C7 because if we see from the before clocking if at the last counting down, with the present is C high, D high, E high, F, G high. So if we see at the last at the counting down, we present the 6, and if we continue to counter up, we will present 7 because from the 6 we will present 7 because the up counting. So that's mean the car is leave from the parking lot. So the result we check is correctly at with the state diagram we make it. Impact of the project on the community. Enhance a parking lot efficiency by providing real-time slot availability, reduce congestion, and for attention among drivers searching for parking lot, helps in better traffic flow management in parking area, can be implemented in mall, office, and other public space for improved vehicle organization.
Novelty. First, utilizes JK flip-flops for efficient counting, reducing the need for complex combinational logic. Second, implements a 3-bit binary encoding system for each section, making the design modular and scalable. Third, design in Cortex-2, ensuring a practical and digital implementation of the counting system. Fourth, uses Boolean logic simplification and Cardinal map to optimize the design.
Discussion. First, overview of the parking lots counter. The objective of the project was to design a parking lot counter system that's tracking available parking slot across the 4 zones A, B, C, and D, each with 7 parking slot. The counter decrements when a car enter and increments when the car exit. Transition to state accordingly. To achieve this, the design utilize D flip-flop or JK flip-flop for the state transition, but in this circuit we're using the JK flip-flop. Push button as input for up for entry, down for exit, and two 7-segment display to show the number of the available slot, the number and the alphabet for the available slot.
Conclusions. The project successfully creates a parking lot counter using JK flip-flops. It offers an efficient and simple hardware-based solution for real-time parking slot tracking. Why effective? Minor issues such as propagation delays require additional debounce logic. The system can be further improved by integrating digital display or IoT-based enhancement for real-world applications.
So now we start for the alphabet A because now at the zone A and the 7 parking lot. So that means the parking lot is full. No car. That means the full car. So that's mean a 0 car. So this is for counting up and then for the counting down, and this is for clock. We use the clock. What we call?
Clock trigger.
No, clock trigger. As what we say not automatic clock lah. Okay. So if car enter the parking lot, we get A6 because parking lot will decrease. So it back to the A5, A4, A3, A2, A1, and A0. So that's mean the parking lot for A is full. So start to B7, and B7 will be B6, B5, B4, B3, B2, B1, B0. So it's mean the B0 is already full. And we go to C4, C7 because they're now at the zone C and have a 7 parking lot. So it will be car enter the parking lot, get the C6, C5, C4, C3, C2, C1, C0, and the last zone on the parking lot we get we make it as a D. So D7, D6, D5, D4, D3, D2, D1, D0.